Hi, AP Calculus students. It's Miss Culver. It's the Sunday before Thanksgiving, and I kind of set up my studio here. We won't always be on a whiteboard, but there's some problems that it's great for. I'll also be trying my writing tablet, things like that. But today I got my living room set out, wanted to make sure I had enough light, wanted to see if this works out for you. I am asking you to take a look at this video. That would be the morning, I believe, of Monday the 23rd or Tuesday the 24th. You do have some asynchronous time before we start recording at 9. Again, that'll rarely happen, but just trying to get us on course. So let's take a look at 3.1. So we're going to look at these notes here. You'll take these notes. The examples that I have listed here, we will do that during our synchronous time next week. So sorry, Monday, Tuesday, the 23rd, the 24th. For me, it's next week right now. All right, let's take a look. So I'm trying to learn the best place to stand. This is looking good. Okay, so in 3.1, what that chapter is on extrema. Those are maximum and minimum points. And so basically, we kind of already talked about this. Remember, every time we drew a tangent line where there was a maximum or a minimum, that we found that the tangent line had a derivative of 0 there. So we're going to be working with that a lot. And plus, that's what we do in our life. We try to minimize our costs, maximize our resources. So chapter 3 is application of derivatives. There's no new rules you're going to learn. You're just going to be applying what you already know. So let's take a look. Number 1, the definition of extrema, that is on page 164. If f of x is on interval I, so we'll be using that I a lot, containing an x that equals c, then here are the definitions of a minimum and maximum point. You may be like, well, I know one when I see one, but of course in calculus, we have to be very detailed about what a minimum and maximum actually are. So here's what a minimum point is. A minimum is at x equals c if f of c is less than or equal to, this is very important right here, any other value of the function at any other x for all x on I. Okay, so if you put a c into the function and the function value is less than any other function value for any other x on I, it's a minimum, or equal to. Meaning that if you have a lowest function value, a lowest y value at 2 different x's in the interval, they are in fact both minimums. There can be more than one minimum point. So of course a maximum, if you put a c into the function and that function value is greater than or equal to any other function value at any other x, then that x equals c must be a maximum point. Again, notice that because of the equal sign, there can be more than one maximum point. So if there's highest y values in more than one x value on the interval, they are both, or all 3 or all 4 maximums. The extreme value theorem, the EVT, we'll be using this a lot, just like IVT that you were using. This is also on page 164. If f of x is continuous, very important right here, on a closed interval AB, then f of x has both a maximum and a minimum on I. Notice it doesn't say anything about a derivative, that it has to be differentiable or anything. The function just has to be continuous. And when you think about that in real life, that kind of has to be, right? If you have a function that is continuous, like these two here, somewhere there has got to be a maximum value. Somewhere there has got to be a minimum value, and they can occur at more than one place. Okay, so notice that this function here is continuous, right? On a closed interval, here's the minimum point, there's the maximum point. Okay, here's another continuous function, right? On A to B on the closed interval, here's a minimum point. Here is 2 maximum points right here. Notice I made a not example. Here is a non-continuous function. Notice that there is a minimum on this function. This closed in circle here. Notice though, there is no maximum, okay? Now you may be saying, Ms. Culver, right there, that's a maximum point. Well, that's an open circle though. A minimum and a maximum are actually points, right? This is not a point here. This is an open circle. So the maximum point would be infinitely close to this point, and so we can't say what it is. We cannot say exactly where the maximum is because of this open circle. I just want to point something else out to you too. What if you only had, your function was this horizontal line, right? None of this, right? Just this horizontal line. You may say, well, that's continuous on a closed interval. There's no max or min. Yeah, there is. Because of the equal here and here, right? That means that every point is a minimum. At every x value, isn't it the lowest y value because it's less than or equal to? Isn't every point here a maximum? Isn't that all these y values are equal and they're all the highest y value? And so every point is a maximum also. Weird thought to have. Number 3, definition of relative extrema. Okay. And later on, that'll become more important. What's an absolute maximum and minimum, and what's a relative max or minimum? If there is an open interval, notice the parentheses, I, not an endpoint. So it's an open interval, right? There's not actually any endpoints because there's open circles and you can't mean those endpoints. With x equals c, where f of x is a maximum or a minimum, notice I use different colors, then f of c is a relative max or relative min. Let me say that again, definition of a relative extrema. If there is an open interval, AB, not an endpoint with x equals c, where f of x is a maximum or a minimum, then f of c is a relative maximum or minimum, okay? Number 4, so we'll see that more when we do examples. Okay. Number 4, definition of a critical point. I call that a CP. They also call it a critical number, but I use CP, so I don't have to keep writing out critical point. If f of c is defined and the derivative of c is 0 or undefined, then f of c is a critical point on the function. So what does this mean? This basically means if you've been given a function and they ask you where the critical numbers are or the critical points, you will take the derivative of the function, set it equal to 0, find where that happens or where that derivative is undefined. Those will be your critical points. So something you're kind of already used to. Here's a picture of critical points. So I drew this function here. Notice that at this point here, if I asked you what the derivative is, you would tell me it's undefined, right? That's a critical point. That's a picture of one. Notice at this relative minimum. So notice this isn't the lowest point on the graph, right? The end goes much lower. So this is a relative minimum here, though. Notice if you drew a tangent line, the derivative or the slope would be 0. That's a critical point. Notice here at this maximum point right here, that if you drew a tangent line, the slope would be 0. That is another critical point there. So that's what they look like in a picture. Number 5, if f of x has a relative max or minimum at x equals c, then x equals c is a critical point of f of x. Let's go over here though. Let's continue in green. However, if x equals c is a critical point of the function, a relative max or min is not guaranteed, just possible. So what this means is where you see a relative max or minimum, that in fact is a critical point. It will be a critical point every time. But if you are asked to find a critical point on a graph and you look at it, it may or may not have a relative max or min there. So this is the rectangle and the square idea, right? A square is always a rectangle is not always a square. In this case, wherever there's a relative max or min, that's a critical point. Wherever there's a critical point, there might be a max or min, but it's not guaranteed. right? For instance, here's a cubic function. Notice if I drew a tangent line here, the derivative would be 0, but that is certainly not a maximum or minimum point right there. So what do we do with all this? Here's what we do. How to find extrema on a continuous closed interval. So that's what they're going to be asking you to do. How do you find max and mins on a continuous closed interval? So here's what we're going to do. We're going to find the endpoints first, right? Because it's closed on E to B, we should be able to find f of A and f of B, right? We're going to find those y values. The next thing we're going to do is find the critical points, right? We'll take the derivative of the function, set it equal to 0 or undefined, and see if there's any x's on the interval where that happens. And if we find x's where the derivative is 0 or undefined, we will put those into the function and get those y values out. And then what we do is we just always compare. What are the y values of the endpoints? What are the y values of the critical points? And the highest y is where your maximum point would be. The lowest y is where your minimum point would be. So what we will be doing together are these examples. Have a wonderful day. It's snowing. Really, for the first time, it's looking good. And I hope you're all doing wonderfully. Thanks for hanging out with me.